going to be tonight we're going to be hearing from Anye Shafer, and she's going to be talking about architecting for microservices. I'm going to be posting her social links in the chat so that if you find, and I know you will, if you find the information in this talk helpful, inspiring, you can follow up with her at those designated links. And I'm going to pass it off to Anye.
Thank you very much. Let me get my screen share going and make sure that I can still see the chat. Okay, perfect. I'm not used to Zoom. I'm more used to Google Hangouts. So I'm trying to make sure that I can see the chat. Okay, so just give me 1 second. All right, so sorry about that. Thank you for the introduction. I am Anye Shafer, and I'm here to talk about architecting for microservices. We'll talk about the evolution of software architecture from monolith to microservices, the benefits that you get from microservices, as well as an understanding of who wouldn't actually benefit from them, and why, despite how they're simpler in some ways, they're actually a lot harder as well. We'll cover some best practices and common patterns for microservices. And this slide deck will be available later. So if there's anything on here, don't feel like you got to write it down or anything like that. And there's even some stuff at the end, like resources and some extra comments that I'm not going to really have time to go over, that will be available on the deck for you for later reference. I won't really spend any time on my bio, but the cliff notes are I've been working in app dev since the late 90s, and I've been an architect for about 12 years. Currently, I work for Signify Health as an enterprise architect, focusing on microservices, event-driven processes. But everything I say today is my opinion and not that of my employer. So with that out of the way, let's get to the good stuff. And I apologize for the dog barking. She always has great timing. From monolith to microservices. Cue the 2001 Space Odyssey theme music here. In the beginning, software architecture was pretty simple. Programs were what we call monolithic, meaning one application handled all of its responsibility, be it user interface, business logic, data access. So no matter what you changed, you were basically recompiling, redeploying your applications. Applications tended to get larger and larger and encompass more functionality over time. And as software teams grew, that meant there were more fingers in the same pie. As you've probably experienced, having too many developers in a single code base is a recipe for a coordination nightmare. It's too easy to break something somebody else is working on or have them break what you're working on. Scheduling your deployments, you have to schedule them really far in advance, make sure everybody's work is ready to go. So you ended up with a very waterfall-ish kind of situation. Not fun at all. And let's not even spend a lot of time on how multiple users could use one of these applications when the data was installed basically on the computer with the software. You didn't have any sort of centralization because we only have an hour and I don't want to spend it all on history. So eventually someone had the idea of saying, hey, let's just divide up these applications. So you'd have the user interface living on a user's machine and the data could be centralized. This general pattern we call client server. Client apps run on the user's machine, but the data lives on a server. There are a lot of variations on this theme. The earliest were thick client applications where all the logic lived in the client program and the server just is where the data sat. And that's as opposed to a thin client, which is kind of the opposite, where on the client machine, you just have very simple presentation data, but all the guts and the logic are happening on the server. For thick clients, most of these are things that get installed on your computer, things like the Office suite, or where you had to used to run those nice install shields for 20 minutes and eventually you had a program you could run. Thin clients, more likely to be web-based. So as the web became more popular, we started seeing more thin clients. But there are thick client applications for the web too. Back in the day, we had servlets, wrong one, applets. Applets would install on your, they were programs that would install and run on your machine. And the pendulum kind of swung back and forth between thick client, thin client with various technologies. When single page applications got popular several years back, thanks to Angular, React, Vue, etc. This provided a more sophisticated development experience that could run in the browser. Those apps could be internally quite modular, and they require connecting to one or more external data services, as they can't access databases directly. And I should have been on this slide. Sorry for that. Sorry. Nope. Went too far. Sorry about that. Sorry, I can't see underneath my chat window. Okay. Yeah. Okay. Sorry about that. Okay. All of these historical architectures I've talked about are still valid and they're still used today. The thing about technology is there's no such thing as one size fits all. And sometimes an older design is the best fit for your needs, but sometimes it isn't. With microservices, an application's functionality isn't delivered just by one program or one client app and one server, but by a collection of separate, loosely coupled systems that are independently hosted, independently deployed, have separate code bases, and have clearly defined narrow responsibilities. And they own their own data. Then the user interface applications can rely on these microservices to provide the data and the functionality that drives them. Put another way, the term microservice generally refers to one single deployable unit controlling a limited scope of functionality within a microservices architecture, which is the whole landscape of individual microservices that are utilized and shared by the applications that require the functionality they provide. So on this slide, you'll see a fairly simple example of what a microservices landscape could look like. You have a user interface application that kind of has three internal modules, each of which is calling a different microservice to handle business logic and data access. And each of those has its own database. Now, we'll talk about a somewhat better pattern for microservices than this a little bit later. But this is just kind of a simple, the easiest kind of view that you could have. So as an example, and I'm going to use this example kind of throughout the talk tonight, let's think about an e-commerce site. So, and I'm sure we've all used an online store at some point, especially during COVID. And if you start thinking about all the things that you can do when you're on an online store, they're going to fall into several broad categories. There's user management, the action of creating an account, managing your addresses, your passwords, stuff like that. There's the catalog. You've got to figure out what it is that you want to order. So you browse through categories or you search by, for some keywords to find what you want to order. You view your product details. Then once you decide you want to buy something, you have to go through what I would call kind of the order activities. You add it to your cart, you say how many you want, maybe you go find something else, add it to your cart, eventually you check out and you place your order. And then someday later, you may actually be viewing your order status. And all that's kind of related to orders. I break out payment services as a separate one, just because usually when it comes to paying for things, you're integrating with a lot of third-party stuff. You're like managing credit cards, and those, there's a bit of a difference between actually handling the payment itself and tracking like what's in the order, which is kind of more internal. And there's other things that an online store could do, but this is just kind of a sample breakup. So each of those would be considered kind of its own domain within the e-commerce site. And each of those domains would have its own microservice that provided the functions within it. So this is what that might look like. You've got your user interface that is internally modularized to have the various functions that we talked about. And each one of those calls its own microservice. In this case, each of the microservices has its own database, and two of them actually also interact with external services for authentication and for credit card processing. So what do we get out of microservices? Something, technology evolves, there has to be a reason that it evolved. So why would we use them? And there are a lot of benefits to microservices. Let's see. Since microservices are limited in scope, they are naturally less logically complex, and individually, they require less cognitive load to understand than a monolith. And what do I mean by that? I just mean that from a business functionality perspective, there's actually less in an individual microservice. So if you have a new dev that joins your team, they don't have as much business knowledge to learn. They don't have to learn about all of those domains that we talked about before. They can focus on the one that's in this app. Testing is less complicated because there's less stuff in the app to break. Because it's smaller in scope, there are fewer dependencies, less complicated hosting requirements, and that will lead to somewhat easier and faster deployments. It takes fewer people to manage a smaller service. So you don't have to, usually it's just one team that owns the microservice. So you don't have to coordinate across a bunch of teams to do deployment. And all of those factors together lead to increased productivity. So then the changes that you make inside your microservices won't affect anybody else because they're isolated. Now, it's the contracts, i.e. requests that are coming from another service or the responses that you give to them, and the messages that can be sent around, published by one service, consumed by another service. Those are the touch points where you have to be really careful because you can affect other people if you change those. But if you change the internal details about how you implement something, that shouldn't disrupt any other applications. This also helps you gain resilience. So if one of your microservices is down, that doesn't necessarily bring down your entire application. It might bring down part of it, but part is better than all. And if you're able to set up interactions between your systems as asynchronous, which we'll talk a bit more later, you can gain even more resilience out of that. It makes it easier to use the right tool for the job. Because you have separate teams and separate deployments and separate environments. If there's a reason that you should have one application written in super optimized C++ and then another application written in Python, there's no reason you can't do that. And scalability. You can actually scale your services independently if they're split up. And what do I mean by that? Well, let's consider the e-commerce site again. If you think about those various functions we talked about, user management, catalog, order management, and payments, the catalog probably gets the heaviest use of those because people spend a lot of time searching. Not everybody who comes to the online store is actually ultimately going to buy anything or create an account. So you can basically say, all right, well, let's run twice as many pods with the catalog service that we do with, say, the user management service. And you can have each service just as scaled up as it needs to be to handle the load that it's getting. And that's just cheaper in terms of money than it is to have one big application that you just have to keep scaling up and up and up to meet the needs of one particularly chatty business function within it. And last but not least, security. Microservices can be secured more easily because you can limit access to the entire service to users and systems that are supposed to be there and just not even let anybody get through the front door if they're not. And, you know, obviously we don't want breaches to happen, but clearly you read the news, they do occasionally happen. If a breach gets into one of your microservices, you're exposing less data than if you have a monolith and they get into your monolith database and literally they've opened the keys to the kingdom. So we've talked about a lot of benefits here. And with all those benefits, you might think, shouldn't everybody use microservices? And the answer is absolutely not. There are a lot of situations where microservices are actually more trouble than they are worth. I'm going to take a quick sip because throat's getting dry. If we work in an organization that only has a handful of developers, then you probably don't have a big problem trying to coordinate your builds. Microservices aren't going to help with that. If you're in an organization that doesn't have a mature DevOps and CI/CD capability, microservices would be an absolute nightmare for you. And I say that because you have a lot more provisioning because you have a lot more services, and you have a lot more deployments because you have a lot more services. And if you don't have something like infrastructure as code, like Terraform, to make provisioning really easy, and you don't have automated deployments to make getting changes out easy, you're going to spend all your time on infrastructure and deployments. You're not going to have any time to write code. And what that's going to do is it's going to disincentivize you from releasing very often, and that is detrimental to your progress. So don't do that. And similarly, if you don't have strong infrastructure, networking, site reliability engineering folks in your company, then microservices are not really a good idea either, because there's such heavy reliance on networking with microservices, because of course they're distributed and they communicate across the network, that as soon as anything goes wrong, you're going to have trouble. And the security requirements for going across the network are going to be more complicated. So you just be buying yourself a world of hurt. If you build mostly very, small self-contained applications that don't interact with each other at all, then you don't really get anything out of microservices, because there's nothing to share. You've already got a self-contained kind of discrete unit that doesn't need to be broken down any further. And the last scenario where I wouldn't recommend microservices isn't always immediately apparent, but if you're working in consulting, and someone hires you to build something for them, not only should you think about like, how can we do this job? You have to think about what can the client actually support. And if you've got small business clients that don't really have much of an IT presence, and they don't really have a bunch of people on staff who can do all these things we talked about before, then building them a microservices platform would be doing them a really big disservice, because there's no way they're going to be able to maintain it effectively. So you should never feel bad for saying, I don't think microservices are for me, because they actually are a lot of trouble. And you might say, well, why are they trouble? You just told me all the reasons that they're like so great and they're simple and whatever. But the reality is they are actually a lot harder in a lot of ways. And next, we're going to talk about why that is. So why they're harder is less about what each microservice is responsible for, what it does from a functionality perspective, and more about what's required to deal with distributed systems safely and effectively. When microservices are running in their happy path and everything's working great, yeah, they are simpler because they just have a lot less logic running. However, there's a lot more things that can steer you off that happy path pretty quickly when dealing with microservices, because of the increased reliance on network communications between the services. Some of these aren't immediately obvious. And when you're running your code in the debugger and all of your resources on your local machine and everything's working great, it can give you a false sense of, oh yeah, this system works great. And so there's a concept that's been around for a long time called the fallacies of distributed computing. And what those are referring to are these implicit assumptions that are made if you ignore all these things that can go wrong and that you don't defensively plan around them. If you make these assumptions, quite frankly, you have a ticking time bomb on your hands. And at some point, that app is going to have a problem. So the wise microservice developer plans for them up front, which is actually pretty hard. So I'm not going to go into detail on these fallacies. It's just, there's a lot that's been written about them. I do have some slides in the appendix that go into a little bit more detail, but I'm just kind of, you can see what they are here. I'll, kind of laugh about a couple of them, but basically these are, the assumptions that I said that you'd be making if you don't accommodate for them. So the network is reliable. Well, no, it's not. Latency, also known as lag, is 0. Well, we all know that's not true. Bandwidth is infinite. Again, nope. The network is secure. Okay, I think by now you're getting the idea. Like you might not have thought of all these things when you're focusing on the functionality and the code and how am I going to build it, but like all this stuff is super important with microservices and will get you into trouble. And I'm sure a lot of us here, certainly anybody who deals with microservices, has sat on support calls when, service A can't talk to service B and they're not sure what happened. And it's because someone in the infrastructure group created a new firewall rule that now is like blocking traffic, just all this stuff. Good times. So I highly recommend that you Google the fallacies of distributed computing and like read up on them, because it will make you a stronger, more defensive developer, which is always a good thing. If you're a developer, if you're not a developer, it's like I can make you a developer. But even as QA or as a product owner, it's also important to understand this stuff because you have a good idea of what can go wrong, and your expectations will be set. So there are other reasons that microservices are hard, and a lot of it has to do with the challenges of distributed data. And the first kind of challenge that I'm going to talk about is displaying data across domains. So as we've mentioned, each microservice owns its own data. They all have their own database, which means if you want to show a table on your screen, on your website that looks like this one in the slide, that's showing information that comes from a membership microservice and an order microservice and a support microservice, you can't just write a single query against some tables and join them and say, yay, here's your view. You can't do that because they're in 3 different databases. This is a scenario that's really easy to handle in a monolith because the data is all in the same database, but not easy at all with microservices. So how do we do it? Clearly, we're going to have applications that need to show a view like this. And there are several ways that you can handle it, and they all have some trade-offs associated with them. You could have the UI call all the microservices individually itself and recombine the data when it gets it back. But let's think through this. If it's a lot of data, then you load all of it at once. I mean, that's a lot of data. You got to deal with bandwidth, you got to deal with performance. So say, okay, well, what if we page the data? Well, if you're calling multiple microservices to get pages of data, how are you going to guarantee that you get the same records on each of the pages from different microservices? They might not sort in the same way. And either way, it's going to be bad performance. On top of that, you're making your user interface know an awful lot about the backend systems, and you're kind of violating the separation of concerns principle. So probably not the best choice. You could have the UI call a single microservice and let that microservice call others and aggregate the data to send back to you. That'll take care of the separation of concerns part, but it doesn't really fix any of those other problems. You're still trying to figure out how to get data from a bunch of different places and merge it together, which probably won't be performant. Incidentally, that's what technologies like GraphQL do under the covers. They make it easy for the developers to say, this is the data I want, even though it comes from like 20 different places. But it obscures the difficulty, but it's not going to ever change the fact that it's not going to be super performant. And there are sometimes some some security concerns with that kind of a system as well, that can be difficult. So the most performant option, if you're thinking about having an application that responds quickly and shows that view that you want to see, is of course the most complicated thing to do, which is to find a way to get that data from the 3 or 4 microservices that it lives in all into one database for read-only purposes, like a replica that you could query. And this is actually a really good pattern for the cases where you can do it. It requires a lot of work up front because your choices are really either set up database replication or use events. Using events is probably better, and we'll talk a bit more about that later. But it's, like I said, it's a lot of work. And the other thing to take in mind, or to keep in mind, is it only works in scenarios where you can accept eventual consistency. Because anytime you're relying on data getting moved from the system that owns it to another system that you're going to view it from, there's going to be at least some delay before that data gets there. And if the application you're showing is someone's bank account, they don't want to know how much money they had 30 seconds ago. They want to know how much money they have right now. So it's not universally useful. So the next challenge as far as distributed data goes is what we call distributed atomic transactions. So what does that mean? An atomic transaction is a multi-step process where you need all of the steps to either succeed, or they need to all fail and all roll back. You can't leave it in an intermediary state where, well, the first 2 parts worked, but the second 2 parts didn't, so oh well. Can't do that. All or nothing. In a database, a single database, this is really easy. You start a transaction, you run your queries. If any of them fail, you roll back. If not, you commit. Great. But again, microservices, multiple databases. You can't do that. So what you need to do is you need to figure out a way of handling a logical transaction across a bunch of different systems. And to do that, you need an orchestration. What we mean by that is it's a process that coordinates the workflow that you're going to do. So that multi-step process, you have one process that's basically being the traffic conductor and figuring out what to do. do the first thing. If it fails, roll, then you're done. Do the first thing, it succeeds, do the second thing, that fails. Now we have to go undo the first thing, etc. It manages the flow in both the success and failure scenarios. So if you wanted an example of this, let's go back to our e-commerce site. If you have an order that gets created by an order service, and then the payment gets processed by a payment service, and then it gets shipped by a fulfillment service, all three of those things really need to happen. If there's a problem where one of those is going to fail, then everything needs to get rolled back, because if what they ordered suddenly got discontinued, they already paid for it, you got to give them their money back. So orchestrations can be short-lived. Sometimes it could just take seconds or even less to go through and call all the steps in a workflow and great, we're done, or roll them back. But orchestrations can actually last for like days or weeks. So like think about if our e-commerce site was actually a B2B site rather than a B2C site, and we weren't taking credit card payments, but we were going to be invoicing people, and we're like, okay, well, you have 30 days to pay your invoice, and then we're going to ship. So like the orchestration may actually be very long-lived. So there are a lot of technologies available for helping to build and manage orchestrations. Some of them are very code heavy. Some of them are more like COTS packages where you can kind of build a workflow from steps and then kind of customize them a bit. There's a lot of different options, but they're complex scenarios, and the APIs are in your services that are the individual steps. If you're not doing something that's like completely like out of the box, they have to support operations that both do something and then undo something, so that the orchestration can tell it, okay, go do this. Nope, go roll it back. The orchestration doesn't do the actual work. It's just directing the traffic. So let's see. If I haven't completely scared you off microservices yet, and I hope that I haven't, let's talk about some of the best practices for building them. And because we have only a short time, I am by no means saying that these are the only best practices, but there are a few that I think are pretty important. So each microservice should be limited in responsibility to a single business domain. Limited scope is kind of the micro in microservices. And similarly, we don't want to repeat ourselves, the dry principle. You've probably heard that. But both single responsibility principle and dry are not just for microservices. They're good practices in general, but they're particularly important here. You don't want to have multiple microservices that are implementing the same thing. If you've got multiple applications that need that similar function, then they really should be utilizing one microservice to do it. Now, there are some exceptions. If you have similar functions where the data is actually very different and the rules are very different, it may make sense to implement something like that twice and keep the data separate. Kind of my rule of thumb is, are they more similar or are they more different? If they're more similar, then I would have one single microservice that only enforces the global rules that are shared across everybody who's going to use it. And then those things that are a little different, those specialized app-specific rules, let the applications enforce those for themselves. Okay, I say this a lot, and I will probably say it more times before this talk is over. Microservices own their own data. Thou shalt not connect to someone else's microservice database. If you put a connection there, someone's going to use it. And all access to the microservices data, especially if you're editing it, should be through that microservice itself. If you're consuming it, you can also consume it through events, but we'll talk about that later. And one of the reasons that that's really important is uniformity. If only that microservice edits that data, you know the rules that are being applied to do so. But also it fits in with the ability to use events to communicate between microservices. So it's a best practice to have a microservice broadcast the changes to the data that it owns, so that other services that need it can consume it. At a minimum, you could use it to potentially populate your data warehouse and avoid having to set up physical data replication from the databases, which of course would have somebody connecting to your microservice database, which we're trying to avoid. but it also allows other microservices that need that data for their own purposes to consume them. And that could be just to build their own store, like we talked about. So they have a read-only copy of this data because they need to join across it for their own queries. Or it could be that they need to act when certain things happen with certain kinds of data. So they can consume the events to start a process on their side. And it's nice because it keeps the responsibility separate. The publisher of the event that owns the original data that's getting changed doesn't need to know how everybody else is going to react to that, because it's just saying, hey, I did this data changed. If you care, great. If not, that's fine with me. And there's a few different ways that you can accomplish this broadcasting. You can publish the events directly through code programmatically. But there are also passive connectors that you can use that can basically like pull your data and create the events for you. One example being Confluent connectors that work with Kafka. Okay, loose coupling. Loose coupling just refers to systems that don't know too much about each other and aren't joined at the hip. They're not, one of them is not physically dependent on the other to do its function. They might be logically dependent, but they're not physically dependent. And by nature, synchronous calls, like API calls, will create a tighter coupling between systems than communication through messages will. That's not to say never have synchronous calls. That would be absolutely ridiculous. UI applications require synchronous calls to function properly. You know, most of the time when you're displaying a bunch of data on the screen, you got it by making a get call, which is synchronous, and pulling the data back and showing it on the screen. That's totally fine. And there's other times where, you know, you make a call to create some data or edit some data where you need to know right away what the results of that operation were. One example, getting back to our ubiquitous e-commerce example, is if you're managing the catalog and you create a new category for products, the logical next thing you're going to do with that is put products in it. Well, you can't put products in it if you didn't get like what the ID of that category is that you just created, because you probably mostly know how relational data tends to work. So when you create the product category, you want to get back a response that says, yep, I created it, here's the ID, have fun. But that's not always the case. There are lots of situations where you might create some data that you don't need to use immediately. You don't need an immediate response. All you really need, in some cases, you don't really need anything. In other cases, you just want an acknowledgement that, yep, I got the request. I'll do it and I'll get back to you later. The more that you can rely on these kind of asynchronous or at least partly asynchronous communications, the more loose coupling you can have. And that gives you some resiliency. So consider a situation where you want to request let's say it's a product get created, but you don't need to use it immediately. If you were to send a message that says, hey, go create this product, then if the product catalog service were down, it doesn't matter. You can still create that request to create the product because all you're doing is throwing it in the queue. And the service, when it comes back up, will just go pull the message from the queue and it will do it then. But if you're calling directly to the product service to say, hey, create this product right now, you can't do that if the API is down. So again, it's not always feasible, but you should be looking for situations where you can get away with looser coupling and communicating through messages. Oops, too far. So, honor thy contracts. Message and API contracts, which are, like we said before, the touch point between different applications, different services, should change in non-disruptive ways. You want to maintain backwards compatibility so that you don't break things. And luckily, there are some rules of thumb that are fairly easy to logic out and how that works. So if you're going to change an API request and you're going to say, all right, I'm going to add the ability to support some new function. So I'm going to give you a new flag on this API request. Well, make it optional, or at a minimum, assume what the default value is so that a consumer that's calling this API that doesn't know that you changed it isn't going to break. They'll just get whatever that default behavior is. And similarly, when you're returning a response for an API, don't delete fields from the response. Consumers may be relying on them and you'll break them if you do that. Now, we all know that there are some cases where things happen in the business and you just can't avoid it. You're like, I've got to make a breaking change. The way that you want to do that is create a new version of that endpoint, like increment the version number, mark the old one deprecated. New consumers can go straight to the new version. Old consumers get a little bit of time to upgrade. Changes to event formats can be a little bit more complicated because sometimes the change is being driven by the consuming app that needs something. And sometimes it's just being driven by the publisher that says, hey, I'm going to give you something that you might not even care about. So there's actually backwards compatibility, forwards compatibility, full compatibility. There's a bunch of different ways that you can track it. And you can use something called a schema registry to manage your message contracts, to try to ensure that the changes are made in a way that is compatible with your policy, and so that a consumer can say, I'm looking at version X of this particular schema, I'm expecting version Y. This is what I know how to do about it. On the API side, there are some API technologies that actually can help you enforce contracts as well, like gRPC with Protobuf. But even if you're not working with any of those, even if you're just using, doesn't even matter what technology it is. These are principles that you can apply to just be thoughtful about how you make changes so that they are less impactful to the systems around. So services should be isolated, both in terms of how you host them and how you deploy them. By hosting them separately, you create simpler environments. And you don't risk having conflicting needs between applications. So like if you try to install two applications on the same virtual machine or even real machine that require different versions of the same library, okay, this is what we used to talk about. If you ever heard anyone talk about DLL hell, that's what they're talking about. You don't have that with segregated deployments because you just put out what you need and you don't care what anyone else needs because no one else is there. You also have less risk of having one process starving another process in terms of resources, like hogging the CPU or memory. If your databases are on a shared server, they share the max number of connections, and one of them can basically hog all the connections and the other one doesn't have anything left. So there's a lot of advantages to splitting them up, and not least of which is if something goes wrong with that particular server, you only lose one application, you don't lose, or one service, you don't lose everything. So Dockerizing your environments, basically, or containerizing, is an automated way that you can, specify what is needed to host a particular application, and kind of do it programmatically. And frameworks like Kubernetes help you manage these containerized deployments. So if you have containers of apps that are being deployed in segregated deployments, these are faster, they're simpler, and you don't have to coordinate nearly as much with other people or worry about what's happening with other apps. And being able to have more frequent deployments helps teams achieve what they call fast flow. And that's kind of a buzzword, but what it really means is they're able to react quickly and make quick changes and get those changes out the door really quickly, and iterate. Agile, another thing that I'm sure you don't live under a rock, and you know about the idea behind Agile, which is just being really responsive and being able to iterate through change very quickly. Make a small change, see how it works, adapt if that's not what they wanted, or if it didn't work the way you wanted to, make a quick change. Doing that is going to be so much easier when you have segregated deployments that are fast. Feature flags. Feature flags also help enable fast flow, because they let you turn features on and off in real time, oftentimes without a deployment even. And they also let you release a feature to just a subset of users. So you could actually like test in production, or have a set of like special users who will evaluate a feature and say, yeah, this is something we want to release to everybody, or maybe this didn't work right. It also, and this is something that's been really helpful for me personally, in my work, it helps coordinate big releases that cross multiple teams. So multiple domains. So because even though we segregate by business function, a lot of times, your business landscape, these different functions do have some connection to each other. And if you have a big initiative that requires work from several different teams, and you can't just put one piece out there because that would affect the other pieces that might not be ready yet. Using feature flags is great because each of the teams can do their work on their own schedule and release it basically turned off. So the code will be sitting out there in production and that particular code path won't ever get executed until everybody's done their pieces. You've gone through the full testing in the lower environments. Everybody's like, yep, this looks good. And you literally flip a switch to turn it on. And if it doesn't work, you flip the switch and you turn it right back off again. So it really helps mitigate risk. Honestly, there aren't that many scenarios where feature flags are not helpful. I mean, there are some, but I almost think it's better to assume that you're going to need them and figure out the cases where you don't than the reverse. But it's really important, if you do use feature flags, especially if you use them as liberally as I think they should be used, is that you need to remember to clean them up when you're done with them because your code will become this big mess of, if this flag is this, then do this. Also, if this flag is this, then do this. And you'll just have flags everywhere. And this is actually a real scenario. I had a new tech lead come in, inherited a team and a bunch of apps, and there had unfortunately been some turnover, and he's looking at all these flags and he's like, do we need this? Do we need this? Do we need this? And I'm looking at him, I'm like, okay, most of these features have been live for over a year. If you actually turned these flags off, you would cause a problem. So yes, my recommendation is when you ticket a feature and say, hey, this is the story we're going to do, create the story to get rid of the feature flag once it's fully validated in production. And then your code will stay relatively clean. There are a lot of vendors that provide feature flags and related functionality like A/B testing, stuff like that. You could build it yourself, but it's probably not the best use of your time unless your job is providing feature flag technology. Okay, so let's talk about some common microservice related patterns. We are nearing the finish line here. Okay, API gateways. So an API gateway is a service that sits in between the consumers and the underlying microservices. It verifies the authorization, who's allowed to go to the services they want, and then it'll route a request to where it needs to go. If you have APIs that are externally facing and not just internal to your organization, you really, really need an API gateway. Because you don't want the general public seeing your internal API landscape and having paths within your internal network. And also, it'll simplify your security. You don't want every single microservice that you're ultimately delegating requests to have to know the details about all your individual customers and who has what and who's allowed to do this and that. An API gateway can handle all that for you. It's great for just general security, because if someone isn't authorized at all, then you can block it at the gateway level and not even get the request down to that underlying API at all. I see a question coming in, so I'm going to stop to give you a quick. Should one microservice, another is a writer, CQRS is signal microservice. I'm going to come back to that a little bit, Raul. But I wasn't saying that the entire microservice had to be read-only, but if you have an application that is displaying information across domains and you have some of that data your domain might own, that application's kind of like affiliated domain might own, but some of the information might come from others, then in your domain database, or a database that just belongs to your application, it's kind of a toss-up which way you do it, you can have read-only tables, basically. So you always own the data from your own domain, but you can pull data in from other domains to use for reading purposes. Now, you can have a completely separate read-only database. There's no reason that you can't do that as well. But I wasn't saying that the microservice itself had to be read-only. I mean, there's honestly, you can do it a bunch of different ways. Does that answer your question? Okay, cool, thanks. All right, so back to API gateways. I was talking about how they're great if you, or actually how they're pretty much essential if you have external facing clientele. But even if you have only internal domains, or sorry, internal users for your APIs, the API gateway is still pretty useful because your UI applications can still have a single service to call and not have to know all the details of multiple connections to different services. And just with the external case, you can have your API gateway be the one to handle the security as far as which services are allowed to talk to each other. There's a lot of service mesh kind of technologies that can also, help with that. But one thing to keep in mind with this API gateway pattern that is extremely important is that an API gateway is a single point of failure. So if you're using one and it goes down, nothing gets through. So you need to make sure that your API gateways are rock solid if you're using them. Now, fortunately, all the major cloud platforms have API gateway offerings, and there are also other third-party vendors that you can use if you happen to be like doing on-prem stuff. But so don't bake your own if you can avoid it, because you really want it to be like super solid. A variation on the API gateway pattern is the Backend-for-Frontend API, aka the BFF, or your UI's best friend. A BFF is a service that's tailored to a specific user interface that takes all the requests from that UI and sends them where they need to go. So that kind of sounds like an API gateway, but the difference is that it's for one UI. So if you had an application that has both a web client and a mobile client, each of those could have its own BFF. And even though they're doing the same kinds of things and they're hitting the same underlying microservices, the way that they prepare the data for their channel would be a bit different. So for example, you might return much smaller data structures for a similar query for a mobile app, or use a smaller page size, just because of the additional bandwidth limitations and smaller screen size on a mobile device. But you can use a BFF even if you only have a single UI per application. And we do this where I work. And another reason to use a BFF in that scenario is to simplify data access for the user interface. This is especially great if you have different people acting as your UI developers versus the backend developers. It's probably less crucial when you use full stack folks, but it's super useful if you have front-end specialists, because they don't really have to know like all the details about, these are the 20,000 configuration settings that you need to call this one API. And these are the ones you need in this scenario. And these are the ones that you need in that scenario. And like, they don't care. They want to design the UI. So it's very common with a BFF pattern that you expose, like one endpoint per function, basically, that the UI is doing. And you may have several endpoints in your BFF that ultimately call the same microservice endpoint, but they're doing it with different configuration options, different parameters for different purposes. The BFF is where that complexity is known and handled, and the UI is completely shielded from it. We kind of touched on this before. The BFF can act as an aggregator of data for multiple microservices, but you should be careful about doing that with tabular data. That tends to work a lot better if you're looking at a single record, so to speak. Like you've got a person and you want to get different kinds of data about that one person. Then those calls to those other APIs are more like an individual get by ID kind of query. And those are a lot faster than trying to like meld tabular data from multiple sources. Okay, let's talk about retry policies. And retry policies help us mitigate fallacy number one from a few slides back, i.e. the network is not always available. Well, the fallacy is that it is available. The reality is that the network is not always available. And transient errors do occur. So a retry policy basically says, if something fails, let's try it again. And then maybe try it again a couple seconds later. But what you want to do is you want to configure it to handle different kinds of failures in different ways, because some errors, any of you who work with HTTP status codes from your REST APIs, or any API for that matter, that there are some status codes that mean you could retry this till the cows come home. It's not going to help you. if the caller sends a bad request or anything really in the 400 level errors, they don't have an access token or they are forbidden to do the function they're asking for, retrying is not going to help. So you want your retry policy will say, if you get an error like that, just fail fast, immediately return, nope, can't do it, sorry, have a nice day. But other kinds of errors could potentially be transient. They could resolve quickly. So your retry policy would say, all right, if it's this kind of error, then try again immediately. If that doesn't work, wait this many milliseconds till you try again, and then maybe double that time, etc. You specify how many times you're going to retry and how long to wait in between them. But the thing to keep in mind is, if you're talking about synchronous calls that you're handling, don't wait too long, because while you're retrying, your consumer is hanging and waiting for you. So it's kind of a bit of a balancing act. Usually what I like to do is, when in doubt, I will assume that an error that I don't know what it is transient, to retry it, unless the consequence of failing is actually less than the consequence of having bad performance. And that can happen. In that case, you can just make the opposite assumption and fail fast unless you know it's a transient error. So the retry policy has a cousin called the circuit breaker, which also helps you handle types or situations rather when the network is down and a resource can't be reached. But this is for situations where it's going on a little bit longer. So basically what a circuit breaker says is, all right, I keep trying this, it keeps failing. Let's just wait a while and give it a chance to resolve itself before we try again, so that the consumers that are waiting for me to do this don't just keep hanging while I wait. And under the covers with a circuit breaker, you tell it how many failures in a row will result, do you need to have before you break the circuit and you stop trying for a while, and how long you should wait before you try again. So once that failure condition happens, say you configured, if it fails 5 times, then we're going to break the circuit. So it tries to call your database 5 times and it fails. Well, actually, let's not use database for this. It tries to call this API 5 times and it fails. So now if you've configured to say, wait a minute, don't make any calls within that 1 minute. So within that 1 minute, you have choices. You can basically program what you want it to do. So in the case of you're trying to call a database or you're trying to call an API, you may have to just fail fast and say, sorry, we can't do that right now. We'll and then the user can try the operation later. But there are other circumstances where you actually can have some fallback. It's pretty useful. So let's just say that you have a cache supported application, and that most of the time, the data that you're sending back to the UI is coming from something like Redis or Couchbase, some kind of cache. And if your cache is what's failing and your circuit breaks, you can fall back to the database and get the data there. And maybe you don't want to have to call the database every single time you're querying data that you use all the time, and that's why you're using a cache to begin with. But it's better to go, if you have a couple minutes where there's some blips, it's better to call the database and get the data that way. Now keep in mind that doesn't work quite as well for cache write operations, because if you fail fast on a cache write, then that stale data is gonna remain. So you might want to leave kind of a background thread trying to reconnect to that cache and get that data updated, or have some method of telling the cache that data has been invalidated when it comes back up. But that's a more complicated scenario. But anyway, back to the circuit breaker itself. Once the waiting period elapses, the next time that resource would be called, it's going to try again. It'll say that the circuit is half open. It's going to try again. And if it succeeds, then the circuit gets closed. Normal behavior resumes until, of course, you have that series of multiple failures again. If that first time it tries after the waiting period, it still fails, then the waiting period will start over. It'll wait that amount of time again before it tries again. So the result of this is that your user experience is better, because they're not constantly just hanging on these requests that are taking too long. So that is the end of the content that I have as far as what I'm going to talk about. I did put together some, where's it go? Too far. Some links to various articles from people who are smarter than me and wrote some really good stuff on a lot of the topics that we talked about. And I also put a shameless plug to my Medium blog, which I don't update nearly often enough, but every once in a while. And also, as I mentioned at the end of the deck, there are some more discussion about fighting the fallacies of distributed computing. So thank you very much for attending this talk. I really hope that I've given you some things to think about as far as when to use microservices and how to use them, and just all the things that you have to consider when you build them. And I would be happy to take any questions now that you have on this topic or anything else that you're interested in.
I have one.
Sure.
So when you were talking about the things that can go wrong with microservices, which did you learn firsthand? And
oh gosh. Oh gosh. We're actually having a lot of problems with resources going down and taking down the whole app. Like, so gosh, there's so many production problems that we've dealt with at various points. So we had services that were depending on multiple other APIs, and we had health checks going that said, like, if this goes down, it should take down the whole app because nothing's going to work. But if this other thing goes down, let's just say that the service is degraded and, like, post the link. Well, we had a situation where we thought we'd built the application so that if the cache went down, it was like, it shouldn't have mattered. We thought we had all these like try catches in there. So, like, if we're trying to read from the cache and we can't do it, then it's just going to fall back to the database. Everything's hunky-dory. But it ended up not working out right. Like, what was happening is, like, our Redis cache was, like, getting too full, and it wasn't able to write any new data. And it was like it was actually taking the whole app down. And it took us a while to figure out what's going on. And quite frankly, I can't even remember what was going on, because I've slept a few times since then. But, like, I see a lot of time, like, there's you've got a channel at work where people talk about, like, what's going on in production right now. And there's a lot of, like, this API is down. Like, so, fortunately with microservices, that one API being down is probably not taking everybody down. But, every business does have some, like, critical components that, if that goes down, it has a measurable impact to the business. So having some kind of fallback to avoid that is huge. And, like, we're working on a system right now where the whole point of it is to do a lot of calculations up front, not in real time, so that we're not having to put as much load on a database, which is starting to strain under huge amounts of load for, like, real-time calculations. So that's the whole loose coupling thing. Like, if you can do the calculations in advance and then query the data that's already kind of ready for you, then you have a little bit of wiggle room. Like, some of the services could actually go down for a short period and no one would notice because everything got prepared in advance, and you've got a bit of lead time before the critical system runs out of data to deal with, if that makes any sense.
Yeah, that makes sense. Thank you.
Mm-hmm.
I really appreciate your presentation and this topic. And, I'm a fairly new developer, and I was wondering more about the flags.
Okay. Did you have a particular question, or do you want me to explain more, like, what they are,
or maybe how they're used? I'm imagining that you're like, okay, a flag might be test, or a flag might be this, goes with this new API.
Okay, I can give you an example. I'll just talk about, like, the technology that we use currently where I work now, and it's called Launch Darkly. So basically, there's a web UI. It's a vendor. You pay for the service. It's a web UI, and you go in and you say, I want to create a flag, and you give it a name. And you say, like, what kind of flag it is. It can, most of the ones that we use for the purposes of toggling things on and off are Boolean flags. They're either on or they're off. But you can also have a flag that has, a list of states that you're processing right now. Like, if you're doing it, we did a slow rollout of something recently where we started with just a couple states, and then we started adding states to our Launch Darkly flag. And as we added them, then our system started processing. It was receiving events, and events were coming from various states. It had been ignoring any ones that were not in the filter, but in real time, without doing a deployment, we could say, okay, we're going to do Texas now. Boom. We put Texas up in Launch Darkly. and suddenly our app is processing it. So how that actually works under the covers is basically with sockets. So at startup, a connection is made between your application and LaunchDarkly, and that socket connection is open. And it tells it, or you tell it basically what flags it cares about. And if you go into the LaunchDarkly application and you change the value of the flag, that open socket that new value gets pushed to your application. And now your application's folding into memory. But when you start it up, it grabs the value that LaunchDarkly had at the time that you started up the app. So every time you could have a flag that's getting evaluated hundreds of thousands of times a minute, and it's not calling the LaunchDarkly server every time it needs to evaluate the flag. It's sitting in memory in your application. But when it changes, it's being pushed via an open connection to your application. So that's why in most cases with something that works like LaunchDarkly, you don't have to actually redeploy to change the value of flag. Now, there is an exception, and I have dealt with this. If the thing that you're turning on and off is something that is registered at startup, then even if you change the LaunchDarkly flag, you already registered it, or you already didn't register it. It's not something that is actually like, you can't turn on a service that you register at startup if it's not already turned on. So for those scenarios, LaunchDarkly doesn't buy you anything more than just having an app setting in your environment variables but you can redeploy. You don't necessarily have to change the code if you rely on environment variables that are picked up by your deployment pipeline. You can change the environment variable and redeploy, and that change will pick up. That's definitely better than having to actually go into your code repo and change a value, and then put in the pull request, merge it, send it all the way through. That's going to take a lot longer. So in your code with LaunchDarkly, like I said, you register the connection with LaunchDarkly at startup, and then wherever in your code after that you care about what that flag value is. You use a LaunchDarkly SDK client, basically, that you've injected into your project, that to say, okay, what's the value of this flag right now? And it uses the value that's in memory. Does that explain does that answer your question?
It certainly helps. Thank you so much.
Yeah, of course.
I just have a quick follow-up on that. So the way you're describing the feature flags, can it be used like while we are shipping certain feature to cohort the requests, for example, like since you mentioned A/B testing?
Yeah, like I haven't personally used LaunchDarkly for A/B testing, but I know that they have the ability to basically, you can import a list of users. So when you evaluate the flag, it requires, at least with LaunchDarkly, obviously other vendors will work differently. It requires you pass a user ID with it. Now, a lot of the stuff I work on are backend services. There is no user. So we'll just basically like pass the name of the application, and we're not using that functionality. We're not saying do it different if it's Joe Smith versus if it's Jane Smith. We're just saying, use the value of the flag that you have. But the user targeting function would let you actually have different behavior from different users. And you could even do tests and prod with a backend service if the user, quote unquote, that you passed in was something that you had attached to a variable that you switched. So you said like, okay, if I say you have a event listener that starts a process, and there's a field on your event that's like application ID. If you and normally the events are coming from your ordering service, just making this up. If you published a test event where you change the app ID from ordering service to production test, you could potentially have production test be a user that you registered in LaunchDarkly. So then LaunchDarkly would then serve up a different value of that flag, which again, it could be a Boolean, it could be a list of states, it could be a date. We actually use LaunchDarkly for cutoff dates, where we say like, if there's any data that is dated before X, we're assuming it's old and we have to go do something new with it. So there's a lot of different ways you could use it. Honestly, we're not using like even half the stuff that they offer right now.
Okay, cool. Yeah. Thanks for answering that.
I guess is a more general question in the terms of your career and working in kind of like this subspace of microservices. What do you think has been your proudest achievement so far? Or one of them?
Gosh. Gosh, that's hard to say.
Which you can also come back to that.
No, I know it's like I don't know. Like the stuff that we're working on, like currently, kind of comes to mind. Like we're in the process of basically like completely changing how we do a major part of our business, and we are trying things that we have never tried before at my organization, and it has been a ride, honestly, because the first idea that we had did not go quite as planned. The concept was there, but it didn't perform. And so we have had to be very creative and iterate and iterate and iterate. And quite frankly, sometimes I think they're getting kind of impatient about some of the iteration. But like what I'm actually really proud of, believe it or not, is my team. So that has been like working on this, because a lot of the stuff we're doing was like really scary. Like they'd never done anything like this either. And I'm like, hey, I've got this great idea for how we can totally change how things work. And I have no idea if it's going to work or not, but hey, let's try it. And the team has learned so much, and they've just done a fabulous job, and they've worked like super hard. And so I honestly, kind of what I'm proudest of is like how I've helped grow this team. And they're really quite a joy to work with. So
Yeah, that's awesome. Are you currently, do you currently have capacity for mentorship, or is that not something you're open to for the time being?
I'm certainly open to it. Like on any individual daily basis. Obviously, some days I've got more time than others, but like the main reason that I got involved with New Code fairly recently, honestly, is just because I'm fairly high up in the, technology, tree, so to speak. And I meet so few women in roles like mine. And that makes me sad, honestly. I know that women are capable of anything men can do, and probably better in some cases. And, I don't believe that it's because women aren't interested. And I want to see more women succeed. And so, yeah, absolutely. If there's someone who's, earlier in their career than I am, and there's any bit of, mentorship or advice that I can provide, like, that's why I'm here. Like, I want to help other people achieve what I feel like I've achieved.
That's awesome and good. That's really exciting for either anyone who's watching currently or whenever the video is posted, for those to see that later. Just putting out like a clarion call, I guess. I guess if anyone has any final questions, whether it be this particular like topic or in regards to Annie's career, feel free to either put them in the chat or unmute yourselves. And we're coming up to the end of the hour now, so we're going to be signing off in just a little bit.
One more question about just your career in general. So I've recently moved in a position where I'm more like oversight, technical lead. How much hands-on are you still, and how have you adapted if you're not? Because I'm really struggling with not being hands-on as much as I would like to.
So at the moment, the kind of hands-on stuff that I do is I'm in an architecture team where there are 6 of us or 7 of us, and we do maintain some libraries. We also maintain what we call architecture templates that are basically, we're a .NET shop, so they're basically skeletons for different kinds of applications that have examples of all the plumbing that we use. So for example, we have a domain API template that has the plumbing for calling other APIs, for getting the security token if it needs it. It's got Kafka publishing and consumption, and like all the logging, and like all that stuff is like baked into this template. So I do hands-on work for that, and for some of the libraries that we maintain. I do a lot of solution design, where I kind of act as sort of glue between kind of the business and product and the engineering team, and like say, all right, this is what they say they want. This is how we could do it. And I'll put the design together. In those cases, I'm probably not building it. Just where I work, architecture isn't technically responsible for production code, so to speak, except for these helper libraries that we do to kind of like make the developer's job easier. And as far as how I deal with it, like, honestly, I do miss being hands-on. Like, I'm not gonna lie, there are days when I'm just like, I just want to sit here and code. But the reality is I do spend more time in meetings, talking to people and problem solving and looking across different teams for, oh wait, you're gonna do that, that's gonna break these folks over here, let's get you guys talking. You know, I do a lot more of that. And I enjoy it because I personally am motivated by problem solving. So as long as I feel like I'm really being helpful, then it doesn't bother me as much when I'm not hands-on. But I do really enjoy the coding as well. So it sometimes is a struggle, kind of like really wanting to be involved in like driving where we're going, but also missing like getting the fingers dirty.
Yes, thank you, ditto.
Mm-hmm.
So you said you trained up your team with, you know, kind of to adapt to this new project, this overhaul of your current system. What did that currently look like? You know, what did that look like? Does that mean, you know, you spend a couple hours pair programming with them and just, you know, walking them through different frameworks, making sure that the right people were teaching the right things to the right people?
Well, there's a lot of stuff. I'm with that particular team, I'm more involved in pull requests than I am with most of my teams. Because of kind of the special nature of just, we're doing stuff that none of them done. But there's also just a lot of discussion. Like, I also sit in on like the refinement sessions where we talk about the stories and like the designs. And I do a lot of diagrams, and, you know, people just, they just come to me with questions. I mean, you know, or I'll, you know, they'll be talking about something in Slack and I'll be like, I'll just point something out. You know, or, you know, some like, and a lot of times like the QA person will be like, hey, I found this problem, what's going on here? And I'll be like, well, did you look at this? You know, or, you know, the business will say, hey, I'm getting a report that this thing it doesn't look right. I'm like, well, have you looked over here? You know, so it's, and the other thing I think that actually has made a really big difference is I kind of like, I worked really hard to cultivate a culture where actually actively critiquing pull requests is a good thing. Like, you work with some teams, and even though, yes, there's a policy, there must be 2 approvals on every pull request, you see that like the same person approves every PR 30 seconds after it's submitted. And you know that they're not actually reviewing the code. But on, you know, this team that I've been working with for a really long time, like, that's not a problem. Like, anyone on that team will call anybody else out and be like, you know, and not mean, but they'll be like, hey, you know, should this be like this, or did you forget this? And they'll do it to the lead, they'll do it to me if I happen to like be putting in code for something, you know, I mean, which I don't always do, but you know, and that, I think that's a really good thing. Like, everybody on the team has good ideas, and everybody on the team, no matter how senior you are, misses something occasionally. And it has to be considered a good thing to find problems before they make it to production. But not everybody sees it that way. And that's a shame.
Well, that sounds like a really healthy work environment. That sounds like one that I think all of us would want to be a part of, or like, you know, have that, you know, be an inspiration that we can try to pull into our own teams. So thank you so much for sharing this. And really, your presentation was very insightful, and I know that we all enjoyed it and our time with you today. Thank you so much for presenting again. I'm going to go ahead and close out the call, and yeah, great job, Annie. I really appreciate you speaking with us today.
Thank you all so much for coming.
All right, I'm going to post her socials once more in the chat and close it out. Have a great night, everybody.
Thank you, Annie.
Thank
Thank you,
you.
Annie. Thanks, guys.
Bye.